Consider the set A, which is a set of all X, such that X is a student of class 11 presently studying in a school. We can go to the school and count the number of students presently studying in class 11 in the school. Thus, the set A contains a finite number of elements. We now write another set B as follows. B is a set of all X, such that X is a student presently studying in both classes X and 11. Thus, the set B contains no element at all. Definition 1. The set which does not contain any element is called the empty set, or the null set, or the void set. According to this definition, B is an empty set, while A is not an empty set. The empty set is denoted by the symbol phi, or empty curly brackets. We give below a few examples of empty sets. Let A is a set of all X such that X lies between 1 and 2, and X is a natural number. Here A is the empty set, because there is no natural number between 1 and 2. Let us take another set B, which is a set of all X, such that X squared minus 2 is equal to 0, and X a rational number. Again, B is also an empty set, because the equation X squared minus 2 is equal to 0 is not satisfied by any rational value of X. Let C is a set of all X such that X is an even prime number greater than 2. Then C is the empty set, because 2 is the only even prime number. Let us take one last example. Let D is a set of all X such that X squared is equal to 4 and X is an odd number. Then D is an empty set, because the equation X squared equals 4 is not satisfied by any odd value of X. Let A is equal to 1, 2, 3, 4, 5. B is equal to A, B, C, D, E, G. And C is equal to men living presently in different parts of the world. We observe that A contains 5 elements and B contains 6 elements. How many elements does C contain? As it is, we do not know the number of elements in C, but it is some natural number which may be quite a big number. By number of elements of a set S, we mean the number of distinct elements of the set, and we denote it by the cardinality of set S. By number of elements of a set S, we mean the number of distinct elements of the set, and we denote it by the cardinality of set S. The sets A, B, and C given above are finite sets, and the cardinality of set A is equal to 5. The cardinality of set B is equal to 6, and the cardinality of set C is equal to some finite number. Consider the set of natural numbers. We see that the number of elements of this set is not finite, since there are infinite number of natural numbers. We say that the set of natural numbers is an infinite set. Definition 2. A set which is empty or consists of a definite number of elements is called finite otherwise. The set is called infinite. Consider some examples. Let W be the set of the days of the week. Then W is finite. Let S be the set of solutions of the equation X squared minus 16 is equal to 0. Then S is finite. Let G be the set of points on a line. Then G is infinite. When we represent a set in the roster form, we write all the elements of the set within braces. It is not possible to write all the elements of an infinite set within braces, because the numbers of elements of such a set is not finite. So, we represent some infinite set in the roster form by writing a few elements which clearly indicate the structure of the set followed or preceded by 3 dots. For example, 1, 2, 3 ... is a set of natural numbers. 1, 3, 5, 7 ... is a set of odd natural numbers. ... minus 3, minus 2, minus 1, 0, 1, 2, 3 ... is a set of integers. All these sets are infinite. Note that all infinite sets cannot be described in the roster form. For example, the set of real numbers cannot be described in this form because the elements of this set do not follow any particular pattern. The condition x minus 1 into x minus 2 is equal to 0 implies either x minus 1 is equal to 0 or x minus 2 is equal to 0. This gives us the possible values for x. X is equal to 1 or x is equal to 2. Since both 1 and 2 are natural numbers, the elements of the set are 1 and 2. This set is finite because it has a limited, countable number of elements, specifically 2 elements. The condition x squared is equal to 4 implies x is equal to 4 or x is equal to minus 4. This gives us the possible values for x. X is equal to 2 or x is equal to minus 2. We are looking elements where x belongs to the set of natural numbers. Natural numbers are typically numbers like 1, 2, 3, etc. While 2 is a natural number, minus 2 is not. Therefore, the only element from the solutions that belongs to the set of natural numbers is 2. Conclusion: this set is finite because it has a limited, countable number of elements, specifically 1 element. Now let's solve the next question. The condition 2x minus 1 is equal to 0 can be solved for x. 2x is equal to 1. X is equal to 1 divided by 2. We are looking for x belongs to n. Natural numbers do not include fractions. Therefore, there is no natural number that satisfies this condition. The set is the empty set. Conclusion: this set is finite because it has a limited, countable number of elements, specifically 0 elements. The empty set is always considered finite. Now let's solve the next question. A prime number is a natural number greater than 1 that has no positive divisors other than 1 and itself. Examples of prime numbers are 2, 3, 5, 7, 11, 13, and so on. The set is 2, 3, 5, 7, 11, 13, 17, 19. Conclusion: this set is infinite. Euclid's proof and many other proofs demonstrates that there are infinitely many prime numbers. Therefore, we can never list all the elements of this set. An odd number is an integer that is not divisible by 2. When considering natural numbers, odd numbers are 1, 3, 5, 7, 9, and so on. The set is 1, 3, 5, 7, 9, 11. Conclusion: this set is infinite. We can always find a larger odd number by adding 2 to the previous one. There is no largest odd number, meaning we can never list all the elements of this set. Given two sets A and B, if every element of A is also an element of B and if every element of B is also an element of A, then the sets A and B are said to be equal. Clearly, the two sets have exactly the same elements. We consider the following examples.